we could publish in this journal. But we are now having some evidences, some other results. We are trying this work because this was the first time electrochemical triplet nitronium hypothesis, I should tell, and with some experimental evidence. I didn't talk here the detailed computation and other study because for the time permit, I would like to show generation of another, reactive intermediate azomethanol. This was a chemistry what I did during my PhD, and I wanted to dedicate this work to my PhD supervisor when we started doing electrochemistry. That from the bisilylate species, we are using a silver 1 fluoride to single electron oxidation and generate azomethanolide. We thought if you can do this electrochemical anodic oxidation, generate the non-stabilized azomethanolide, and we did we could do it because this mechanism is very simple. First is undergo a 1 electron oxidation, it formed radical cation, iminium the cation, then due to beta silicon effect decellulation happen, then again oxidation, again decellulation, give the azomethanolide. This is very reactive species. It has to be trapped in situ because this is non-stabilized azomethanolide, and we could trap with variety of examples, and yield was not that great, but because of compatibility with the electrolytes and other things, but we could show variety of scope of this reaction. We could do scale up, because we have done in gram scale also to make this compound. That's the mechanism. As I told in the beginning, one single electron oxidation, decellulation, iminium, imine, then another oxidation, iminium, then decellulation, azomethanolide, and which undergo cycloaddition reaction. So we have discussed generation of varieties of reactive intermediate. Then I will come to CH functionalization, and means arene activation. Okay, so in this, what I wanted to tell means we are overall what we are doing electrochemical CH functionalization. Okay, so this can be these three things can be done. You see, if you take a aryl group, we have a aryl group. We are doing 1 electron oxidation at anode. Then this is very selective. It goes to para position. Why and how? I'll come to the next work. The nucleophile can come here, and then deprotonation and oxidation. Then overall you can get this species. So what is happening? This hydrogen is functionalized with a nucleophile, or you can take an alkyl group. Similar way, if you do cathodic reduction, the radical anion, electrophile can attack deprotonation. Overall, you can get a aryl paraselective functionalization. Or you can generate a radical. You can generate a radical, and you can add to the double bond. This is not so-called functionalization. It is the addition reaction. I'll come. We have some very interesting result on this front. Now, in today, what I will be talking, basically, take simple phenol, do electrochemical oxidation. We have made paracetamol, we have made sulfoxide analog, and we have made spirocyclic dienodes. And very recently, yesterday, this paper appeared in Organic Letter. We have done, selective this functionalization and making this type of molecule, naphthalene fused molecule in asymmetric way. These four work quickly we'll discuss, then I will come to our recent work. So if you go through the literature, you'll see the paracetamol. All you know, the paracetamol is a every pocket drug. In the corona time, it became a very, very useful drug. The Dolo became a drug of everybody. And you see, if you go through the global need, the need of this one is increasing because there are a lot of infection, inflammation, and other things. But this is the commercial methods for synthesis of paracetamol. I'm not here to tell you that I will have a method which will be very cheaper. Making it cheaper on all depend on further engineering. But you cannot disagree with me that these particular methods are generating lot of wastes. And this waste is getting accumulated and it is becoming a threat of our future generation. So that this point of time, we thought, if you see all the cases for getting this amine, we need to use nitro some way. Okay. So we thought nitrogen source is coming in different way. So we thought if we can start this synthesis, this is paracetamol, take phenol, and if you see the carbon numbering, this can come from acetonitrile. So what was our, and see phenol, as I told, it can be selectively oxidized at para position. I'll come with the example how selective it is. And acetonitrile, this is retarded reaction, it can give this part. So we can combine these two chemistry, do anodic oxidation and nucleophile. We can do this, make this reaction happen taking acetonitrile as a solvent or as a reagent. And this role of moisture is very, very important here. Because if you use external water sources, we have done water sensitivity experiment and we show the moisture present in HPLC grade acetonitrile is sufficient enough to drive this reaction, give this oxygen. If you use external water, some equivalent and all, this reaction becomes sluggish. As you are talking, the paraselectivity. See, we block the para position here in the phenolic things. And we, instead of ortho things, it happened in the cost of dearomatization, we got this product. And we could make different analog of paracetamol in this reaction. What is the mechanism? See, and this phenol got anodic, oxidized at anode. It formed this radical. I'll come in next slide that there is radical. There are a lot of chemistry, but we have set the reaction condition such a way this radical get further oxidized to form this cation. And you know, this is stabilized by these two double bond and it goes here only. And acetonitrile attack, then hydride shift happen, aromatization, moisture present in this solvent attack. This is retarded reaction. It keeps paracetamol. Now we wanted to go to different nucleophiles, sulfur analogs. We have some result on this because what we wanted, we are still trying to make different drug classes. So as I told, this radical intermediate, this chemistry is well explored. I'll come. This chemistry, what I discussed in the case of paracetamol, this chemistry is very interesting and less explored. Professor Wortgobel has done a lot of these radical couplings and all synthesis of biaryl and all. But his potential and our potential is different. So we are working that it gets further oxidized 2-electron pathway and it for cationic intermediate so that external nucleophile can be used to trap this and do different chemistry. Other case, it was acetonitrile as a nucleophile and all. Here we have used external nucleophile and this benzyl group is very, very important. We have done extensive study. We wanted to introduce a sulfoxide here. No, and this sulfoxide is in our potential range, it doesn't oxidize to sulfone. It has to be oxidized separately. So this chemistry we could establish, but yield was okay. Still we are working on it. I'll just show you can see the yield is around 60%. We have made different analog, different type of substitution. And we have done different mechanistic study, radical scavenging study, byproduct detection. We could detect that phenol is getting generated. And we have made this compound. Then we have oxidized in electrochemical condition. So this is forming fast, then it is getting oxidized. It is not getting further oxidized in our range. We have done divided cell experiment. So only in anodic chamber when we are putting our reaction mixture, it is getting oxidized. So it is a oxidation process. So we have done time-based experiment studies also. So electricity has to be turned on throughout the reaction. No radical chain propagation is happening. This is the CB. You see, this is phenol. Now you see when we are using base, and then in that case only the catalytic current and all is increasing. Presence of 2A enhance the catalytic current. So this mechanism up to this is fine. You have discussed. Now this you see this benzyl group is needed because when sulfur lone pair is attacking, it is forming this species. Now the moisture present is attacking in SN2 fashion. It is generating the benzyl alcohol. If you are using disulfide or thiol, this reaction is sluggish. So that's what this requirement up to our standardization, this is our understanding. So then it is forming this species, as I told you in our control experiment, it is getting oxidized and it is giving the sulfur. Now, our interest was in urea moiety, we have published this work with hypervalent iodine. But when we started doing electroorganic chemistry, we thought this type of urea, we can do phenol oxidation in presence of a base. It can go, intermolecular cyclization to give spiro type urea moiety. And but I'll come, unfortunately, why this compound didn't give us good activity. This chemistry, I'm not going in details because this chemistry is almost similar what I have discussed. Only here the internal nucleophile is available. We have done extensive study on the substrate code. Yield are also reasonable, and we have done separate control experiment. This is the mechanism, as I told. This phenol oxidation, then this position, and the base which is generating from HFIP, it takes the proton, internal cyclization, giving this product. What is interesting in my interest was, we have done in gram scale, we wanted to debenzylate it. And this will be a urea, which is a spirocyclic urea having different type of backbone and steric demand. And you see, this is a very interesting compound. This aryl group, we put a strategical bromo group, we did egg coupling, we made this compound. We confirmed it from X-ray. What we wanted to, these two type of skeleton, debenzylate and test it in our design protocol. But this debenzylation, varieties of condition, it failed. Then student has to go ahead, and we didn't try further. But this with O-benzyl, this molecule is inactive. So we are still working on it. Now I'll switch my things towards asymmetric electroorganic chemistry. So asymmetric electroorganocatalysis. So it can be that electrochemistry and organocatalysis, these are, there are some method known where Lewis base or Lewis acid or chiral Bronsted acid, this has been used in terms of in electrochemistry. And there are some interesting chemistry coming out where the anodic surface, there are some chiral immobilization. Then electron transfer process can be controlled in phase selective manner. But that type of work doing is little difficult in our lab currently. So what we thought, we will collaborate with some group where we can with that type of catalyst, we can do asymmetric electroorganic catalysis. So we collaborated with Bizu group, group, where he has made different type of NHC catalyst. So NHC catalysis normally known for their Ompulung catalysis, where there is no oxidation. The Breslow intermediate, it is give, you see this, you know that this will be Ompulung because the electrophile will attack here. Normally it was a nucleophilic carbonate. But afterwards, what it came, that's oxidation of this Breslow intermediate to acyl-azolium. Now, if you have a chiral backbone, then your nucleophile can give the facial selectivity. You can do some asymmetric catalysis. But this oxidation or still day was done by chemical or photoredox catalysis. NHC, Breslow intermediate, oxidation by chemical or photoredox catalysis generate the catyl radial intermediate. But when we have started doing this, there was only single example using electroredox catalysis, oxidation of the Breslow intermediate, generate the ketyl radical and do asymmetric synthesis. So we have taken this challenge and do extensive study. The idea was, you take a aldehyde, NHC will form Breslow intermediate. It will undergo 2-electron oxidation to give the acyl-azolium species. Then if you react with 2-naphthol, it will give this 3+2 annulated product. So with this, we have done this reaction. The yield are very good. We got 93% yield, 99% E, and we made several examples. Hydrogen is the only byproduct, and this particular catalyst gave us the highest enantiomer selectivity. As I told, we made several examples. We varied the aldehyde part. We varied some of the yield. If you compare with the chemical oxidants, the yield and enantiomer selectivity is more in electroredox catalysis. Okay, so that was things. We made different. Use different phenol derivative. We could functionalize with different natural products. So the what is important was the mechanism. So this is the reaction what we are doing. So we are doing, see, if you are using tetrabutyl ammonium iodide. Hello, anything else?
No, please carry on. Please go ahead.
Okay.
Please go ahead.
So if you are using tetrabutyl ammonium iodide, yield is good. If you are using and yeah, how much time I have, Professor? Hello.
You can take another 5 to 8 minutes.
Okay, I'll finish by the time. Okay, so if there is no iodide source, we are using BF4, so that yield is decreasing. So if you are using 80% of BF4 and 20 more percent of tetrabutyl ammonium iodide or Ki, yield is reaction is going. So that means iodide ion has a role. So we have done a divided cell experiment, so that is oxidizing things. So it come to the mechanism. So what is happening? See, this is the aldehyde, and it is forming Breslow intermediate in reacting with the NADC. Now this Breslow intermediate is undergoing single electron oxidation first. If in electrochemical condition, if it is a single electron oxidation, please remember, if it undergo continuous 2 electron oxidation, it should give directly acylazonium, and then phenol will attack, and this overall reaction will give this product. But it is not happening without iodide. So iodide has a role. So iodide radical is generating in anode. This is attacking here, and now it is simple. This is coming, and I minus is going away. So acylazonium is forming. So the triazolium NaC without iodide assistant, it cannot oxidize from Breslow intermediate to acylazonium. Iodide is needed. Okay, that was the interesting part. We have done extensive study. We have done Cramswell experiment and all. This is the another thing. The metal catalyzed functionalization of a olefin. It can be done in different way. Quickly, I have to go because But if we do electrochemical way without external radical sources and all, that double bond has to oxidize. Then either oxidize to give radical cation, or reduce to give radical anion, and radical cation case nucleophile can trap, it can get functionalized, or in radical anion case electrophile can attack, get functionalized. But what we thought, if we can take a external, we generate, suppose this type of diketone, deprotonation, radical generation, and it why it looks very simple, but our results are very interesting. It is this we have not published. We are going to publish it now. This addition and give this type of product. Now you see the interesting part. If we have a double bond where there is no radical or cationic stabilization, there is a CH. You see here. There is an alkyl group or a aryl group. If there is an alkyl group, we are getting a product where double bond is shifted. If there is a radical stabilization group or cation stabilization group, we are getting this bifunctionalization product. So this now you see, this is very interesting. This part is getting cleave here. One is another end, and with the oxygen from the water is very important here. It is forming the corresponding benzoate in another place. So we have made varieties of example. We have done a lot of study, and we came to our substrate also. with a strain ring attached here. We got this bifunctionalized product with Lewis acid. It gives this type of. I'll come to the mechanism now. So what is happening? It is generating the radical. It is adding here. It is forming the stable benzylic radical in presence of phenyl. If there is a CH2 group, what is happening? That it is getting oxidized, deprotonation, double bonding, shifting in externally. Now, if this is getting stabilized, it is forming carbocation. Then this one of the oxygen is attacking, forming the oxonia. Now, what OH minus, which is generating an anode, it is attacking. Then this bond is cleaving. Now see protonation. Now we have a species which is bifunctionalized. This particular double bond which was here, and now the interesting part is, if we treat now, we have now result. Treat now with a Lewis acid. It is undergoing a rearrangement to give this species. It is a very interesting molecule from organic material point of view. We can control if we oxidize it. We get a aromatic ring, and we are putting a electron withdrawing group here. Now we are controlling the aromaticity of this ring beaten on the electron withdrawing power of this. So this interesting chemistry we are doing. Now if we are using a base, that result I didn't show. If this is getting enolized here and it is attacking here, it is forming a spiro donor acceptor cyclopropane. Again, it is coming to our domain to do further study. Now quickly I will come to strain ring chemistry. I'm not going in details. What is the important, interesting chemistry of cyclopropane? It is a stable, kinetically stable molecule due to the interorbital ring 104-degree bond angle. We have done extensive study on Lewis acid or Bonsted-Harris catalysis ring opening. Nowadays we are doing photoredox, electroredox catalyzed ring opening. We have written a review before going to this. So this part we have reported. End center radical we have reported. This we have reported. Now we are working on single electron oxidation. Quickly I will come to this part, and these are the things we have reported. This is keto hydroxy compound. Actually, this work we are doing a aryl activation, donor acceptor cyclopropane, and